Hi, this is Mr. Cho, and we're going to continue learning Chapter 7. Okay, so today we're going to learn about models of expansion and contraction and models of changes of state. Let's jump right into it. Okay, so at the end of this section, you should be able to answer the following questions. How do we use models to explain expansion and contraction? And how can we use models to explain why mass is conserved during expansion and contraction? Now, this here is a hot air balloon. I'm not too sure how many of you have ever sat in a hot air balloon before, but I think that most of you will be at least somewhat have some idea how a hot air balloon will work. So, when the air in a hot air balloon is heated up, it will expand, and what will happen to the density of the air in the hot air balloon? That's right. The density of the hot air would decrease. And you have often heard this statement, hot air rises and cold air sinks. So this hot air that is in the hot air balloon will start to rise up because the atmospheric air around it is more dense compared to the less dense air inside the hot air balloon. And therefore, the hot air balloon will inflate up and it would go upwards. Okay, let's just take a quick look at how it works actually. So over here, we have a hot air balloon, and when you heat the air up to 100 degrees, then the balloon will start to climb up because you are decreasing the density of the air within the hot air balloon. So whoever invented the hot air balloon has calculated that if you heat the air up to 95 degrees, that would mean that you will get roughly equal buoyancy as the atmospheric air at a nice height, okay, at the height that you want to be at. And if it is any less than 95, right, which is about 90, then the hot air balloon will start to descend. You want it to descend slowly, you don't want it to crash all the way to the ground. Okay, so the basic idea here is that when you heat the gas particles in a hot air balloon, right, the particles spread out, they expand, and therefore they decrease their density, and the hot air balloon would rise up. Okay, so we just use the particulate nature of matter to explain how the expansion of air within a hot air balloon can help it to function. When matter gains or loses heat, the particles will change in their movement and arrangement. So when you gain heat, you will result in expansion, whilst losing heat will result in contraction. Now this here is an example of something that you will commonly see at a bridge. So if you have been on a bridge, you'll notice that there's certain portions of the bridge where there's actually some gaps in between. Now why do you think the engineer has designed the bridge in such a way? The reason is because when the sun is shining down on the bridge, and the bridge, which is mostly made out of metal, it will start to expand. So if it does not have this spacing in between, then the bridge would buckle and it would break. Okay, so this here is an example of what happens if something is not very well designed. So as we can see, these rail lines are made of metal, and when the sun is shining and it's hot, they start to expand. But because there's no gaps in between, there's no space for the line to expand, and therefore it starts to curve, and obviously your train will not be able to pass through such a track. Okay, so that is expansion and contraction. Okay, so how do we understand these two processes is to study their respective models. And what happens to matter during expansion and contraction? So we need to zoom in to the microscopic level or even the atomic level to understand this. Okay, so we have some models of a particle in solid during expansion and contraction, and let's look at it. Okay, so this here is a model of a solid. As you can see, these small little lines indicate that the solid is still vibrating. Okay, so it's important to remember that even though you don't see a solid move, the particles are still vibrating. Okay, so what happens when you heat up a solid? They will gain energy, right? And remember that heat energy is closely related to kinetic energy, right? Or the movement. So when you heat something, they gain more energy, the particles become more excited, and they start to move more vigorously. And because of that, they start to spread out. Now they still maintain their orderly pattern, and therefore you wouldn't see this solid suddenly change shape very drastically, right? It just become a bit bigger. So the pattern still remains. So when matter is heated, the particles gain energy and vibrate more vigorously. And so the particles move slightly further apart from one another, and this causes the volume of matter to increase. Okay, and this process is called expansion. Now, conversely, what happens when there is a loss in energy? So when a matter is cooled, the particles will lose energy and vibrate less vigorously. And so the particles move closer towards one another, and this will cause the volume of matter to decrease. And the process is called contraction. Now remember what the word volume means. Matter within a fixed area or specific area. Now, you may have heard of this word before, absolute zero. And this absolute zero is basically the absence of heat or at zero heat. Most of us on a daily basis use the Celsius as a way to measure temperature. However, this is not the SI unit. Recall that we have learned that Kelvin is the SI unit for temperature, right? This honor is given to the scientist Kelvin for more or less for kind of not say discovering temperature, but studying temperature. So at 0 Kelvin, okay, although I don't think currently that anybody has ever reached 0 Kelvin before. Okay, that means that this is just a theoretical number. I don't think practically on Earth, I don't think that actually is 0 Kelvin. But what it means is that at 0 Kelvin, there is absolutely no heat at all. And because heat is a form of energy, and energy creates movement, creates kinetic movement. So at 0 Kelvin, there will be no, or I wouldn't say no, minimal amounts of movement. Okay, so let's link it back to this one. Okay, so over here, when we see something expand, right, they are gaining energy and they are spreading out. Okay, but when heat is removed from the substance, then it will lose energy and it would it will vibrate less frequently. Okay, so that is because you have reduced the temperature down. Okay, so don't worry about all these numbers, but 273. Okay, this is just something that you can convert easily on Google. Okay, so if you want to find out what is 0 degrees Celsius in Kelvin, just go to Google and it's all there for you. Okay, let's move on and talk about what occurs to matter during not this one. Let's move on. Yeah, so the mass of matter does not change during expansion and contraction. So remember that mass is the amount of particles within substance. Okay, so this did not change, right? The amount of particles did not change. So for example, in this log, we have a metal log here. The amount of particles, let's just say that there's 100 particles. Okay, obviously there's more, billions of particles in, or even trillions in a log. But that's for the sake of simple counting. Let's just say that there's 100 here. Were you to expand this log upon heating, the amount of particles still remain the same. Okay, so if you got 100 here, you still have 100 here, and therefore the mass remains the same. And likewise, when you cool it down and it contracts, the amount of particles still remain the same, and therefore the mass remains the same. So what we can say is that the mass of matter does not change during expansion and contraction. Yes, over here. So during expansion and contraction, the distance between the particles would change. Although the volume of the matter changes, the size and the amount of particles of matter do not change. Okay, so this size specifically refers to each of the size of the particle. Okay, so you will not see this particle suddenly increase size. This size of the particle will remain as it is. Okay, so this particle is this size. It cannot change. So what we can say is that during expansion and contraction, the mass of a matter is conserved. Okay, conserved just means that it does not change. And this phenomena occurs when all matter expands or contracts. Okay, given the example in a steel log, the distance between the steel particles increase when they gain enough heat, but the number of steel particles does not change. Therefore, the mass of the steel log is conserved. Okay, let us now move on to 7.4, models of changes in state. Okay, at any point if you are feeling confused, just pause the video and rewind back to the section that you found confusing. You can even message your teacher for help. Okay, let's move on to 7.4, models of changes in state. So how can we use models to explain melting and boiling in terms of the changes in the state of matter? Okay, so remember, what does melting mean? What does boiling mean? Okay, this is something that you should know, but just for everyone to be on the same page, melting means that a solid becomes a liquid, and boiling refers to the point where the liquid will become a gas, closely linked to evaporation. Now, this here is a picture of a polar bear. What name shall we give him? Let's call him Pinky, the polar bear. And he is currently on a piece of ice. However, his piece of ice is melting, and this is because of global warming. So as a result, polar bears and other organisms are forced to change their feeding habits. That means that they are forced to travel further distances to find food. And oftentimes they fail in finding food and they become starved. So the melting of Arctic ice is an example of the changes in the state of matter, right? From a solid to a liquid, and even to a gas, right? When the water becomes water vapor. Okay, so the terms melting, boiling, freezing, condensation, these are all terms that you must be familiar with. Let's just go through each of them. Melting means that the solid is becoming a liquid. Boiling refers to the point where the liquid becomes a gas. Freezing is the point where a liquid becomes a solid. And condensation is the point where a gas condenses into a liquid. Here is a picture of some ice. And when a solid is heated, the particles would gain energy and vibrate more vigorously. Okay, we have covered this before. So eventually, okay, so what actually is happening? So if we have a solid and energy is coming into this system, the particles start to vibrate. Now remember that the particles are held together by bonds, right? B-O-N-D-S, bonds. Now there's actually 4 types of bonds between particles, but let us just save that for future. Okay, so just keep in mind that there are bonds in between. So when the particle is heated up, the heat energy comes in and it starts to disrupt the bonds. And when enough energy has finally broken the bond, then the solid would change into a liquid state, and therefore we see a liquid. Now remember that this process takes time. It's not instant. Okay, so there is a lag time between a solid and a liquid. Okay, so it doesn't instantly transform from solid to liquid. There's a certain amount of time that it takes for the energy to come in and break the bonds, and then it can become a liquid. Oh yeah, so using this here, when the particles gain enough energy, they overcome the strong forces of attraction between one another. So this was the bond that I was referring to. And the particles will then break free from one another and start to move randomly. So when solid ice is heated to 0 degrees Celsius, it will then melt to become liquid water. So what is the melting point of water? Oh, sorry, not melting point of water. Where's the melting point of ice? Melting point of ice is 0 degrees Celsius. But of course, if you just keep it at 0 degrees Celsius, it would melt very, very slowly. That's why you want to start to increase the temperature to 10, 20, 30 degrees, which will allow the water to melt a bit faster. What is it, water? Ice. Ice to melt faster. And when the liquid is cooled, the particles would lose energy and start to move much slower. So same story. Remember that there are bonds in between the particles, and when you lose heat, the bonds start to get stronger. So the bonds become stronger, and therefore it starts to become more orderly. Okay, so after some time, the particles will return to their fixed positions, and this is the solid state. So when the particles lose enough energy, there's not enough energy to overcome the forces of attraction or the bonds between one another. And so the particles will start to move closer to one another and move less randomly. For example, liquid water, which is cooled to 0 degrees Celsius, will also start to freeze and become solid ice. Now this here can be a bit confusing. 0 degrees Celsius, right? So just now I said that 0 degrees Celsius is the melting point. But at the same time, 0 degrees Celsius is also the freezing point. Okay, so how does that work? It means that at 0 degrees Celsius is the kind of the interface between frozen ice and liquid water. Okay, but when you remove more and more energy from it, then it would become ice. Okay, so lastly, what happens during boiling? When a liquid is heated, the particles would gain energy and vibrate more vigorously. So you can see here that this is a liquid and they are starting to become more energetic and vibrate more vigorously. So the boiling point is reached. Boiling will occur when the boiling point is reached, and then the liquid will change to its gaseous state. So when the particles gain enough energy, they start to overcome the strong forces of attraction between one another. So these particles, right, they have a strong attraction to the particles around it. And the energy that is gained when heat is introduced is used to break up these forces of attraction, okay, also known as the bonds between each other. And when the bonds are broken, then they become free and they can start to move randomly. So what's the boiling point of water? As we all know, it will be 100 degrees Celsius. Okay, remember that we are using Celsius because it is a bit more convenient in day-to-day language, but remember that the SI unit actually is still Kelvin. Okay, science is weird like that sometimes. So lastly, let's talk about condensation. When a gas is cooled, the particles will start to lose energy and start to move slowly or slower. And so the particles start to attract one another and move closer together again. And then the gas will change back into its liquid state. So as the particles move closer to one another, they start to move less randomly, and the forces of attraction become stronger. And when the steam is cooled to 100 degrees Celsius, it condenses to become liquid water. So I think I've talked about this. In the previous example, we said that the boiling point of water is 100 degrees Celsius. But this same 100 degrees Celsius is also the point of condensation. Okay, or what is important is whether you are adding heat into the system or you are removing heat from the system. And that is what affects whether it would condense or boil. Right? If you are adding heat into the system, then you will cause the water to boil 100 degrees Celsius. And if you are removing heat from the system, then you will cause the gas, the steam, to condense into liquid water. This here is a useful graph that helps to explain some of it. Now, the y-axis is temperature and the x-axis is time. So remember that all of these breaking of bonds and changing of state is not instant, it takes time. So let's say that you have a solid here. When you start to heat it up, it takes time, right? So the solid starts to gain temperature, it increases in temperature until it reaches its melting point. And just to be clear, the melting point of each substance is different. Okay, so water's melting point is 0, but this can be different for other substances. Okay, so not everything is like water. Now what happens at this point is that you are at this kind of interface between a solid and a liquid. And if you notice, the temperature doesn't increase any further at this interface. That is because at this point of time, all the energy is being used to break and disrupt the bonds in the solid. So the energy is not being used to increase the temperature anymore. Energy is being used to disrupt the bonds such that the solid will eventually become a liquid. And once all of the bonds are broken, then it can resume the temperature increase. So at this point of time, you will continue as a liquid. Okay, so liquid, the temperature keeps increasing up until it reaches the boiling point, which again, at this point of time, it stops increasing in temperature, and it now is in an interface between liquid and gas. So the heat energy is just being used to break the bonds. It's not used to increase the temperature. The energy is now used to break the bonds in the liquid such that it will become a gas. Only after all the bonds have been broken, then it has completely become a gas, then the temperature would start to increase again. Okay, so I know that this concept can be a little bit confusing, but take some time to digest it. Okay, some links will also be provided to further explain this concept. Okay, so to summarize, right, the change in state of matter occurs only when sufficient heat is gained or lost, and hence the change in state depends on the amount of heat that matter gains or loses. Right? For example, Arctic ice melts because it has gained enough temperature from the rise of the surrounding. And now let us do a summary chart for the chapter. Okay, so we have talked about the particulate nature of matter, and this is actually a model. Okay, obviously, whatever we learn, these are all just models. That means that these are the ways that scientists have thought of to teach students. Okay, and these are described as matter is made up of tiny particles, and these particles are in constant and random motion or movement. Matter is divided into three main groups: solids, liquids, and gases. Solids are closely packed together, and they are arranged in a fixed, regular pattern. They only vibrate around their fixed position. Liquids are close together. They are not arranged in a fixed, regular pattern, and they are able to slide past one another. And so this is actually the reason why liquids can flow. And lastly, gases are far apart from one another. They are not arranged in a fixed, regular pattern, and they move freely over long distances. These three have different properties, right? Such as different abilities to be compressed, so on and so forth. Go and read the textbook. Okay, lastly, the effects of heat gain and heat loss, such as expansion and contraction. Okay, so when you gain heat, you expand. When you lose heat, you contract. Okay, so the volume changes, but mass is conserved. So melting, boiling, and freezing and condensation, this brings about a change in state. And so this brings about a change in state. So be familiar with all of these terms and what each of these terms mean. Okay, so with that, we have come to the end of this lecture. Okay, so feel free to watch it again, rewind, and of course do your SLS or your Google Classroom homework. Alright, I'll see you back in school. Don't forget to like and subscribe. Okay, bye.